Deriving the inner atomic spring constant for a mole of some element. When there is a mass hung from the element, we can think of the atoms inside of this mole of this element as springs. And there are some springs in series and there are some springs in parallel. When springs are in series, they are stretched twice as long, and when they are in parallel, they are stretched half as long, making parallel stronger than series. So, to find the inner atomic spring constant, we know that the spring constant is equal to mass times gravity over the change in L. And to find the number of springs in parallel, we can take the cross-sectional area divided by the density squared. And to get the number of springs in series, we do the length divided by the density. So since the number of springs in parallel is stronger than the number of springs in series, we can write the spring constant as so. Number of springs in parallel multiplied by the spring constant over number of springs in series. Then, if we substitute in what we know for each of these, we will have the cross-sectional area over the density squared times the spring constant over the length over the density. And then we know that one of these will cancel. And then we can solve for the spring constant as so. So the spring constant would be equal to mass times gravity over the change in length multiplied by the density times the length over the area. So given that mass times gravity is force, we can then rewrite this to look like this. So this will now be that the spring constant is equal to the force over the area over the change in length over the length times density. And then this is equal to Young's modulus times the density. And then this can also be rewritten to solve for Young's modulus as so. Which would be Young's modulus would be equal to the spring constant over the density. And that is how you derive the inner atomic spring constant.